Hi, and welcome to your second lesson on one-dimensional kinematics. In this lesson, we're going to go into speed and velocity, what's similar and what's different about them. We're going to start off with looking at what's similar and different about them. And so the first thing we're going to look at is what question do each of these answer? If you remember back to the first lecture where we talked about displacement and distance traveled, what we really focused on was what was different about the question that they answered. In the case of speed, it's just answering how fast you're moving. In the case of velocity, it's answering the question of how fast and which direction you're moving. And the how fast there is tied to the directionality. So you'll see some examples of this later on to be a smaller number in those cases. Speed is a scalar, velocity is a vector. That's why it has a directionality as well as a magnitude or a size. The units are the same though. They're both measuring how fast something is moving, so we typically use meters per second. You might be more familiar with miles per hour. 1 mile per hour, actually, let's flip that around. 1 meter per second is the same as 2.2 miles per hour. So basically, when you see values in meters per second, if you want to get your bearings on what that means, about double it. The equation that we use to solve for these, again, it's going to look similar, but for speed, it's the distance traveled per time, and for velocity, it's displacement versus time. All right, let's look at velocity here. So how do we solve for the average velocity that something has? And the equation is just the change in the position or the displacement divided by the time. One thing that's important to recognize here is that the velocity is in the same direction as the displacement. The reason for this is because the displacement is a vector, but time is not. So your change in position tells you which way something goes. Time doesn't tell you which way it goes. And since that's the only directionality that we have in the equation, then the average velocity must be in that same direction. If something changes its position to be more to the right, then it must have had a speed toward the right in order to make that happen. Another thing I'll point out is that this is actually your first really important equation of the year. Okay, so let's take a look at a nuance within velocity, and that's whether or not we're talking about an average velocity, which is what the equation that I just showed you solves for, or whether we're talking about an instantaneous velocity. So I'm going to start by showing you a graph of velocity versus time. And we're going to look at average velocity first. Okay. Now, if I'm looking at this, something's moving at 2 meters per second and then slows down and ends up moving at -2 meters per second, so speeds back up, but in the opposite direction. I drew a line here which basically just says that on average, we didn't do anything, right? And I'll try to show you why. If I have something that starts here, and it starts off pretty fast and then slows down and stops and then slowly speeds up and gets back to here, nothing happened. It didn't go anywhere. And that's exactly what this graph is showing. It's showing that this object ultimately did not go anywhere. So its average velocity for this whole stretch is 0. Now I can show that in a little bit more of a rigorous mathematical way by just taking an average. So I picked 2 velocities from the graph, and I chose the time equals 0 velocity and the time equals 4 seconds velocity as my initial and final velocities. And so that's 2 and -2. If I add those up and divide by the number of things I'm adding up, in this case 2, then I get my average velocity of 0 meters per second. Now, I'm going to ask you a question, which is what would happen if we were trying to find the average velocity from 0 to 2 seconds? What would that average velocity be? All right, hopefully you answered that the average velocity from 0 to 2 seconds would be 1 meter per second on average. It starts off at 2, ends up at 0 meters per second. If I add those up, I get 2, and I divide by the number of items I'm adding up, which is 2, taking the average of those 2 values. So I end up with 1 meter per second. And if you look at that hits the halfway point, okay? So we can also just kind of look at the halfway point of the interval of time that we're interested in finding the average for, and that is also going to be the average velocity. So again, if I go from 1 second to 3 seconds, you should be able to identify what the average velocity is for that interval of time. Hopefully you indicated that that's going to be 0 meters per second again, as in the first case that I demonstrated for you. because that's what you get when you take 1 plus -1, you get 0, okay? Now that's average velocity, but there's a big caveat with this. This only works if you have a graph, if you have a linear velocity versus time graph, that's when this works. If it's all curvy and wiggly, this is not going to work out at all for you. So only use it in those situations. That linear velocity versus time graph happens to correspond to something called a constant acceleration situation. We're going to learn more about acceleration in the next lecture, but for right now, just keep in mind that this equation will only get you the average if you have a constant acceleration, which includes 0 acceleration, okay? But this only works under constant acceleration. I know I said that multiple times. It's super important. The equation that always works for average velocity is the delta x over delta t from the previous slide. That's why that one's boxed and this one is not. All right, let's take a look at instantaneous velocity now. Instantaneous velocity is just how fast and in what direction something is going at a particular point in time. So if I choose the point for t equals 1 second, I just look at my graph and I can see that that's 1 meter per second. If I instead choose 3 seconds, my time equals 3 seconds, we should be able to figure out what velocity that is instantaneously. All right, and we can just look at the graph and we can see that that is in fact -1 meters per second. All right, so that's just telling us how fast at a particular instant. The initial and final velocities in the previous slide were instantaneous velocities. All right, let's take a look at an example. And this example is going to be as straightforward as we can make it. It's one that you've seen before. So at time equals 0, a person standing at 0 meters. At time equals 4 seconds, the person has, sorry, 2 seconds, the person is now at 4 meters and in terms of their position. So one of the things that we should be able to see here is that if I'm looking at the displacement, that's 4 meters because it's 4 minus 0, and it took 2 seconds. So that gives us an average velocity of 2 meters per second. But there's no way for us to know what the instantaneous velocity is at any point in time in here. We don't know if this person started off slow and sped up and then maybe slowed down again. So they might have reached a speed that was much higher than 2 meters per second before slowing down again. The person could have even moved backwards and then moved forwards. So they could have had a negative instantaneous velocity if they had started going this way and then quick rushed back the other way. We don't know. All we know is this is on average how fast this person was moving, and that this person was moving on average that fast to the right. All right, let's take a look at another example. This one's going to be a little bit more complicated. We've got the person standing at 6 meters. After 2 seconds, the person is at 0 meters. And after another 2 seconds, the person is now at the 2 meter mark. So if we're trying to find average velocity, which do we want to pay attention to? The distance traveled or the displacement? Okay, well, hopefully you said displacement because it's average velocity equals the displacement divided by the time. And the displacement here is -4 meters because we started at 6 and we ended up at 2. So we went 4 meters in the negative direction to achieve that. Now I know that there was lots of other motion in between, but again, change in position doesn't care about all the in-between stuff. It just cares about a starting point and an end point. If this took 4 seconds, then that means that our average velocity would be -1 meters per second. This does not represent the average or the instantaneous velocity at any given point in time. We could also break this up into different segments and identify what the average velocity would be for different segments. So for example, if we went from time equals 0 to time equals 2 seconds, what would be the average velocity of the person during that interval of time? Okay, well, hopefully what you figured out was that the displacement in that case would be -6 meters, and the time would be 2 seconds. So we would use the formula, and we would have -6 divided by 2, and that would give us an average velocity of -3 meters per second. All right, now let's take a look at speed. So for speed, we're interested in the distance per time, and so we need to figure out what the total distance traveled was. And that doesn't care about initial and final positions. It doesn't care whether or not you backtrack. It just cares what is the total path length. And in this case, the total path length is 8 meters, and the total time is 4 seconds. And so that means that the average speed, again, not instantaneous, we don't know if the person sped up or slowed down, but the average speed is 2 meters per second. Also note that there's not a negative sign here. It doesn't care which way this person was going, just what was the total path length. All right, let's do one more example. This is the roundabout, and the radius is still 10 meters, and the distance of 3/4 of that circumference is 47.1 meters, which we solved for last time. And the time that's going to take us to get through here is 5 seconds. So what we're going to do is we're going to be starting off by looking for average speed. So if we're trying to find the average speed here, I've given you the distance traveled, I've given you the time, find me the average speed. Okay, so all you need to do is distance divided by time, and that should be 9.4 meters per second. And if you're trying to convert this to miles per hour, this is a little over 20 miles per hour. And that's it. We again don't know how fast at any given point in time this car is moving, but we know on average they're moving about 20 miles per hour. All right, and now let's take a look at this in terms of average velocity. So I've put my coordinate system here, and because the radius is 10 meters, I can identify where these points are. And in terms of displacement, I can focus on X and Y directions, or I could look from start point to end point. If I was looking from start point to end point, this would be a change in position of about 14.4 meters in the southeast direction. I'm going to just leave it as X and Y displacements though. So we've got the time still is 5 seconds. And what I want to do then is figure out what is the velocity in the X direction. What is the average velocity in the X direction? So we just use our average velocity equation, and we only care about delta X because we're looking at the average velocity along the X axis. And that gets us 2 meters per second. So this is a lot smaller. And the reason for that is because we didn't really effectively move to the right. You know, we moved to the right sort of pretty well at first, but then we came back around and started moving to the left. So that really tells a different story from the average speed. It tells us how effectively did we get somewhere? And the answer is not that effectively, not compared to how fast we were moving. We're moving at 9 meters per second, almost 10 meters per second, but we only moved at a rate of 2 meters per second to the right. I do want to just kind of mention that we could look at this from the standpoint of instantaneous velocities. And if I do that, that's kind of what I was mentioning before. Right here, the car is moving at about 10 meters per second north. And right here, it's moving at about 10 meters per second south. Those would be instantaneous velocities. So the instantaneous velocities can be very different as time goes by, and they can be very different from the average velocity. All right, let's do a quick review. We're going to talk about velocity versus speed. Velocity is displacement versus time. It's how fast in which direction, and it is a vector. Speed is the distance per time. It just answers the question of how fast, and it is a scalar. One thing that I do want to make clear is that the magnitude of the average velocity is not necessarily the same thing as the average speed of the object. And hopefully the last example demonstrated that, right? Like the magnitude of 2 meters per second east is not the same thing as 9 point whatever meters per second as an average speed. And the reason that they're not necessarily the same is because velocity cares about the directions. So if there are changes in directions that take place, then your magnitude of your average velocity is going to be different from the magnitude, well, from the average speed. All right, and the last thing that I want to just review is what's the difference between average and instantaneous. So average velocity is the speed and direction over some finite interval of time. So whether that's 2 seconds, 100 seconds, or 0.1 seconds, some actual time interval passes. And because time passes, the object might move and change position. And so we just find the average velocity by delta x over delta t. If the acceleration is constant and we happen to know two instantaneous velocities, then we can get the average velocity for the interval of time that those two instantaneous velocities bound, as an initial and a final. Instantaneous velocity is the speed at just an instant and what direction it's going at that instant. If you have a graph, it's just the point on a velocity versus time graph. You could also solve for it using this average velocity, this averaging of velocities, along with knowing what the actual average velocity is. But that only works if the acceleration is constant, which it will often be in AP Physics 1, but you shouldn't take it for granted. All right, that's it for this lesson. I hope that you learned something from it, and please take a look at the next lecture on acceleration.